Hello everybody. If you can go and take notes, if you don't have your notebook with you, you can go ahead and put it on another piece of paper, attach your notebook later. I want to back up for a minute. We left off some machines, go back to the inclined plane, because we're kind of going through this very quickly. I know with the rush and really thought we had school today. But inclined plane, remember, is a flat surface at an angle or incline with no moving parts, able to lift objects by pushing or pulling the load. We see the formula we've seen for IMA already, effort distance over resistance distance, but using the L and H for an inclined plane. Remember, L is being the length of the slope, and of course H being the height. So that is the new formula for us compared to the DE over DR. So for this example here, we take our 15 feet, it being the length of the slope here, divide that by 4 feet, which is the height of our inclined plane, and the feet cancel, and we get 3.75 to 1 is our ratio. AMA has not changed. That's still the resistance force over the effort force. And so the inclined plane here, the AMA is going to be our resistance, 50 pounds over 20 pounds. Pounds cancel, and we get 2.5 to 1 as the actual mechanical advantage there. So for efficiency, we're going to have our 2.5 divided by our 3.75 times 100, AMA over IMA, and we get 67%. We said, of course, there's still friction in the system, so that's where we lost efficiency. Now, back to the wedge, talk about how a wedge could be a doorstop, it can be an axe, and like that, anything that's driven into something else to stop it, block it, split it, to raise heavy objects, things like that. Of course, there'll be lots of friction there. Wedge IMA, we go back to DE over DR, effort distance over resistance distance, but once again, that equation changes for us for a wedge, and we have our length perpendicular to height divided by height. So for this example, it would be our length of the wedge, which is 10 inches, and then divide that by 3 inches for the height of it. And so we get the IMA, 10 over 3, 3.33 to 1 is our IMA there. For the AMA, we still use our resistance force over effort force. So the effort here would be the 250 at the top of the screen that we see, and the said yesterday, the 700 pounds goes out equally in both directions, but that's not a double force, it's just a single force of 700 pounds. So that would be a resistance force. So we have 700 divided by 250, the pounds cancel, and left with 2.8 to 1 is our ratio there. So the efficiency of the wedge on the right, well, we divide our 2.8 over 3.333, AMA over IMA times 100, and we get 84%. And this is where we stopped yesterday, but I still want to kind of give a little review since we're going so quickly. A screw really has two components. It's an inclined plane wrapped around a cylinder, forming a path and pitch, and a wheel and axle used to create rotary motion. So it's kind of really a combination of several simple machines, but we get its own category still. Pretty much anything that has threads can be considered a screw. Here they show an example of a piece of triangular paper wrapped around a pencil, giving us pitch in the threads, or you see the threads on this bolt here to the right. Go ahead and you need to write all this slide down. These are very important parts of a screw, the components and the properties. In the blue, properties change rotary motion into linear. I'm talking about the car jack earlier in the example with the picture. How you twist the handle, screw turns, and that there in turn raises or lowers your car if you have a flat. So going rotary to linear. Use a thread fastener, obviously screw, nut, bolt, any kind of fastener that has threads. That's their purposes. Large mechanical advantage. They have huge IMA, put it that way. And then, unfortunately, though, on the downside to screws, they do have a large amount of friction loss. So obviously, every single little bit of surface area on these threads creates friction, and so they do have a lot of friction, and so therefore their efficiency drops tremendously, but they do have a large ideal mechanical advantage. So how do we read threads? So here's basic thread information. It says 1/2 13 NC. The first part, half, is the diameter. That is the very outside to outside diameter of the threads. So we see here in the example right here. So this would be a 1/2 inch. 13 are the threads per inch. So if you were to take a ruler, lay it down, and count how many threads are within that inch, the example has 13 threads per inch. To find the pitch, well, then you would just divide 1 over the number of teeth per inch. So if 13 threads per inch, then picture distance between the threads is 1/13 of an inch. You just put 1 over that number. And that is our pitch. And you see right here, that actually pitch then is the distance between 2 threads. And then NC just gives the thread description. NC stands for National Coarse. Of course, NF would be National Fine. And that just has to do with how many threads are there per inch. Distance, the pitch, once again, is distance between threads and linear distance traveled by rotation of the screw. So for every single rotation of this bolt, the linear distance it travels would be the pitch. So here would be 1/13 of an inch. That's why sometimes it's like you turn a nut or a bolt or a screw forever and ever and ever, and it hardly moves. Well, depending on the pitch of the threads, it could be a very fine pitch, and that's why, because it's not moving that far in a linear distance. And then effort arm distance, if we're not using a wrench, it'd basically be from the center of the bolt to the very outside of the edge of the bolt head, which here is very, very short. That's why it's hard to tighten by hand. Therefore, we tend to use wrenches or tools to use it to make it easier to tighten our nuts and bolts and screws, things like that. But what we're doing by using that wrench, we're increasing our effort arm distance. And how far will a screw with 13 threads per inch move linearly? If turn 1 in full revolution, well, it's 1/13 of an inch. Then when 1 rotation, then it would travel up or down 1/13 of an inch. Screw IMA, we still see the DE over DR, but here we're going to look at the DE is actually 1 rotation of the effort arm or circumference of that. And then the DR, or distance, is a linear distance traveled during 1 rotation of the effort arm or pitch. So the distance between 2 teeth or 2 threads. This one they've changed the example up. This one's now a 1/4 20 NC, so it's a 1/4 inch diameter bolt from outside to outside and 20 threads per inch. So circumference of the bolt will be 2 pi r, and then the pitch would just be P, and so it'd actually be 1 over 20, so 1/20th would be our pitch here for this example. So our actual equation for a screw is going to be circumference over pitch. You'll want to go ahead and write that in your notes right now, and if you want to put it to the side, you can put 2 pi r over P. But the main equation we need for IMA of a screw is circumference over pitch. What is IMA of the screw? Above, if effort is applied by an 8-inch long wrench, well, 8-inch long wrench, we would do 2 pi r, 8 inches being our radius, so we get 50.27 inches. And then pitch, like I was saying earlier, is just 1/20th, so we have 0.05 inches. So 50.27 over 0.05, and we get 1005.3. Huge IMA compared to numbers we've seen before this example. But on the other side, we look at the forces. So we have FR over FE. It's showing that it is going down with a force of 1,200 pounds. An effort on that 8-inch wrench is being applied to 35 pounds. So that's our effort force. And 1,200 being our resistance force. So we would do 1,200 to find the IMA over 35 pounds. Pounds cancel. And we get 34.29. Still a high mechanical advantage, but much, much lower than 1005.3. So to find the efficiency, AMA over IMA, so we have 34.29 divided by 1005.3 times 100, and we get 3.4%. One of the lowest efficiency we've seen this entire presentation. Because once again, there's lots of friction between all those threads and whatever else they're mating with. And back to compound machines again, just remember that to find the total mechanical advantage of a system, then you would take each mechanical advantage individually and multiply them all together. So MA1 times MA2 times MA3, etc. gives your total mechanical advantage. And that's it. You can go and cross the page out if you have your notebook with you, sign the lines, bond the page, and date it. If you have a witness around you, go ahead and have them sign it and date also for you. And we are Dunstable Machines. You will now need to do the packet I gave you yesterday in class, and that was the one. Let me go ahead and pull it up for you. That's going to be the 112 Simple Machine Practice Problems. Do the best you can. I know I'm not there to answer any questions, but if you have questions, you can send me a remind text or email me to my Linmar account, and I'll do the best I can to try to help you while not in person. This will not be due when you walk in. whenever we have class again. But I do expect you to have all you can complete. And then if anybody has any questions, we can answer questions as a class to see if we had any common problems when we return. And then we'll go from there. I'm going to have one more video for you about gears, chains and sprockets and pulleys. Or I forget what the other part of it is, but I'll record that in a minute. I'll go ahead and post these both on PowerSchool Learning, and then you can watch them, record notes, and when we get back to class, we'll hopefully get caught up eventually. Thank you very much. Have a good day.